Hi guys, this is Dr. G here, and in this video we will take a look at some of the practice problems for proton NMR. And in here, especially in this video, I will be using some of the simulated proton NMR data, and then I will show you how to figure out the structure of a molecule using those NMR spectra. And for this study or for this video, I will need you to have a good understanding on the basic concepts that we learned under proton NMR. And also I want you to remember the chemical shift values based on the electronic environment or the chemical environment. Okay, so this actually table is from your textbook. So I kind of want you to have an understanding on how this table works. Especially when it comes to the chemical shift of hydrogens based on the chemical environment. As an example, if you have an allylic group next to a hydrogen, usually it adds about 1. Okay, it basically acts as a +1 to the chemical shift, right? So if you have a electronegative atom, it basically adds 2 to the chemical shift. Okay, so if you have 2 electronegative atoms, it will be +4. So but if you have only 1 electronegative atom, it will add +2. It will add +2 to the chemical shift. And if you have a vinylic group next to the hydrogen, it will add +4 to the chemical shift of the hydrogen. Okay, so that is the understanding that I want you to have when it comes to doing these proton NMR practice problems. And by the way, the chemical shift table that you have in your textbook is missing some of the very common chemical environments, especially when you have a triple bond next to a hydrogen. The chemical shift of that hydrogen is around 2 ppm. So that means it is the triple bond is basically adding a +1 to the chemical shift. Okay, and then aldehydes, the chemical shift for those hydrogens are typically found between 9 to 10 ppm, and then carboxylic acid chemical shift is typically found around 10 to 12 ppm. All right, so once again guys, okay, in saturated hydrocarbons, in sp3 hybridized hydrocarbons, you expect the chemical shift of hydrogens to be around 1 ppm. Okay, you expect the chemical shift of the hydrogen to be around 1 ppm. Okay, so this is our baseline. Okay, so if there are no interesting chemical functional groups around, you expect your hydrogens to have the chemical shifts around 1 ppm. But if you have functional groups such as allylic groups, then the chemical shift will be +1. That means, you will add 1 to the baseline, which is 1 ppm. So that will be around 2 ppm. Okay, so if you have a electronegative atom next to your hydrogen, then it will add a +2 chemical shift. So it will be 1 + 2 ppm, which is around 3 ppm, right? And a vinylic group typically adds around 4 chemical shift values. So it will be around 5 ppm. Okay, it will be around 5 ppm. So these values, the shift in chemical shift is actually calculated from your table. Okay, so when you are looking at peaks, I mean, it is easier to modify the peak using the baseline ppm value. Okay, so we think that the baseline peak is around 1 ppm, and we keep on adding certain values to the baseline ppm value depending on the functional groups around. All right, so let's get to some examples. Okay, so the first molecule that we are going to talk about is isobutane. Okay, isobutane. The skeletal structure for isobutane is given right here. Okay, so actually in here I have given you 2 sets of data. Okay, but I don't want you to look at them now. These are for like verification purposes. Okay, but basically I have the first set of data that I have for the isobutane is actually your proton NMR peaks. Okay, so this is for proton NMR peaks. And the second set of data that I have for isobutane is C13 NMR, okay, carbon NMR, okay, C13 NMR. But I mean, we do not want to look at these values for now, okay. They are just for verification purposes. So let's take a look at isobutane molecule in more detail. Okay, so basically the first thing that we need to do in here is to figure out the number of chemically different hydrogens. The first thing that we need to do is to figure out the number of chemically different hydrogens. So basically the CH3 groups, you have 3 CH3 groups, okay, and all of them are chemically equivalent, okay, and then also you have a CH group in the middle, that hydrogen is also chemically different from the CH3 hydrogens, right? So if you write I'm going to write the condensed formula for isobutane, so it will be a little bit more clear. Okay, so this is how isobutane looks like, and this isobutane has 2 chemically different hydrogens, so you are expecting 2 peaks. Okay, so the first kind is the hydrogen that you have on the middle carbon, and the second kind is the hydrogen that you have on the CH3 groups. Okay, CH3 groups. So you have 2 chemically different hydrogens. So you are expecting 2 peaks in your proton NMR. And the ratio between the 2 chemically different hydrogens is basically 1 hydrogen to 9 hydrogens. So you should see a very tall peak. Okay, the integration should be 9 times greater than the first hydrogen, okay, the peak for CH. All right, so keeping that in mind, let's go and check the NMR spectra. Okay, so in here, as you can see, there are 2 peaks. That is correct. And then also you can see that the taller peak should be responsible for the 9 hydrogens from the 3 CH3 groups, right? So this taller peak should be responsible for the 9 hydrogens from the CH3 peaks, okay? This is from the 9 hydrogens. And then the shorter peak should be from the middle hydrogen, okay? This should be from that middle hydrogen. This should be from that middle hydrogen. And also you can take a look at the splitting patterns, okay? Okay, so the 3 CH3 groups, okay, the 3 CH3 groups have only 1 hydrogen neighbor, okay, so you only have a CH neighbor, okay, so according to n+1 rule, okay, so n that is the number of neighbor hydrogens, so you only have 1, so you are expecting 2 peaks, or in other words, you expect your NMR peak to be a doublet. Okay, this peak should be a doublet. Why? Because you only have a 1 hydrogen neighbor, so this is a doublet. And for the CH, you have 9 hydrogens. So according to n+1 rule, okay, you should see your peak for that 1 carbon splitting into 9+1. So you are expecting it to have a multiplet. Okay, you are basically expecting it to have a multiplet. Why? Because we can never see 10 sub peaks for this hydrogen. Okay, so you are expecting a multiplet for this 1 carbon. Okay, so you are expecting a multiplet. Okay, all right, so that is the analysis for the isobutane. Okay, so you have 2 chemically different hydrogens, okay, the one in orange and the one in yellow. And here's the thing, they are all basically alkane hydrogens. Okay, there is no interesting functional groups next to them, so you can expect the peaks to be around 1 ppm. Okay, so all the peaks should be around 1 ppm. Okay, let's write that down. So this hydrogen should also be around 1 ppm. This hydrogen should also be around 1 ppm. Okay, so the first the methyl hydrogens, okay, methyl hydrogens should have a taller peak, okay, because it represents 9 hydrogens. And then the middle hydrogen should have a shorter peak. And also depending on the number of neighboring hydrogens, you can predict the splitting pattern. So the CH3 hydrogen peak, okay, that has only one hydrogen neighbor. So according to n+1 rule, it is going to be split into 2. Okay, the peak for the CH3 groups is going to be a doublet. And the peak for the CH hydrogen, okay, the middle hydrogen, has 9 hydrogens as neighbors. So it is going to be split into a multiplet. Or according to n+1 rule, it should be theoretically split into 10. But I mean, you are not going to see tiny 10 peaks, okay? So instead you are going to see a multiplet, okay? So this is the analysis. All right, so the next thing that we are going to do is we are going to analyze one more molecule, and then we will go into real-time examples, okay? In here I have 2,3-dichloro, 2,3-diethyl-butane. Okay, so in this example, okay, let's first look at the chemically different hydrogens. Okay, so let's first look at the chemically different hydrogens. So if you want, you can draw the condensed structure, okay, which I'm going to do right now. So you have a carbon. This is a symmetric molecule, by the way. Okay, so we have a CH3 here, a chlorine, and a CH3, another CH3 here, a chlorine, another CH3. So this is your molecule, right? So in here, let's figure out the chemically different hydrogens. So if you take a look at this, I mean, all hydrogens are chemically equivalent. I mean, this is a symmetric molecule, and the chemical environment for all these hydrogens are chemically equivalent. They are chemically equivalent. So you are only expecting one peak. Okay, so you are only expecting one peak. Okay, and where will be the chemical shift? Okay, where will be the chemical shift? So you know, typically we expect the alkane hydrogens to be around 1 ppm. Okay, they should be around 1 ppm. But in here it appears that you have a chlorine. Okay, you have a chlorine in the vicinity. Okay, so you have a chlorine in the vicinity, but the thing is that this chlorine is on a different carbon. Okay, hydrogens are on a separate carbon. Okay, chlorine is present in the neighbor carbon, so this chlorine effect is minimum. Okay, so this chlorine effect is not significant. All right, because of that, you can still expect the peak to be around 1 ppm or maybe 1 to 2 ppm. Okay, so the peak will be around 1 to 2 ppm. So this is that peak. Okay, so you only have one peak. Even though you have 12 hydrogens, you only get one peak. Why? Because you only have one type of hydrogen. Okay, one type of hydrogen, or the chemical environment of all the hydrogens are equivalent. Let's do one more. Okay, let's do one more. So in here I have methoxyethane as the molecule. And let's draw the skeletal structure. I mean, let's draw the condensed structure. So you have CH3, CH2, or CH3. This is the condensed structure for your molecule. And then these 3 hydrogens, okay, are chemically different from the other hydrogens, right? So let's highlight them all. So you have 3 chemically different hydrogens. This is the second kind. The third kind is right here. So you have 3 chemically different hydrogens. Which means how many peaks are we expecting? We are expecting 3 peaks. Okay. And then where will the chemical shift be? Okay. Typically, okay, alkane hydrogens, okay, alkane hydrogens, chemical shift is around 1 ppm. 1 ppm, okay, but these hydrogens have a different chemical shift than 1 ppm. Why? Because the carbon that contains hydrogens is also connected to an electronegative atom. So typically you are expecting it at 1 ppm, but electronegative atoms will add a plus 2, right? So your peak will be around 3 ppm, but give yourself some wiggle room, okay? So we can say it is between 3 to 4 ppm. You can say that it is between 3 to 4 ppm. And then these hydrogens basically have the similar impact. You are typically expecting it at 1 ppm, but that carbon also has an electronegative atom, so it will add 2 to the chemical shift. So it should be around 3 to 4 ppm. Okay, so these are the chemical shifts of your hydrogens. So you are expecting 3 peaks. Okay, the first peak, the first peak should be, the first peak should be around 1 ppm, and the second peak should be around 3 to 4 ppm, and the third peak should also be around 3 to 4 ppm. Okay, 3 to 4 ppm. So these are the crude values for the chemical shift that we can expect for this these hydrogens. And also let's look at the splitting patterns. So you have these two carbons that contain hydrogens, and they are neighboring carbons. These hydrogens are on neighboring carbons. So you could expect splitting patterns. So for this 3 hydrogens, you have two neighboring hydrogens. So according to n plus 1 rule, okay, this will split into 2 plus 1. This will split into a 2 plus 1. Okay, according to n plus 1 rule, the CH3 will have a triplet. Okay, it will have, the peak will be a triplet. So the CH2 hydrogens have 3 hydrogen neighbor. It has a 3 hydrogen neighbor. So basically, according to n plus 1 rule, the splitting pattern will be a quartet. Okay, 3 plus 1. Okay, a quartet. And finally, these hydrogens are actually separated from this oxygen. So you don't have any neighbor hydrogens for these hydrogens. So you can say that this is a singlet. Okay, this should be a singlet. It should be a singlet. All right, so let's take a look at it. All right, so you are expecting a singlet around 3 to 4 ppm. Okay, so that singlet is right here. Okay, this is your singlet. Okay, so this is the CH3 that is on the oxygen. All right, so that is your singlet. And then you are expecting a triplet for the CH3 around 1 ppm. Okay, so this is your CH3. So this is your CH3 that is next to the CH2. Okay, so this is that. And then you are expecting that is around 1 ppm. So the CH2 should be around 3 ppm, and it's a quartet. Okay, so the CH2 should be around, the CH2 chemical shift should be around 3 to 4 ppm, and that's this peak. Okay, and it's a quartet. All right, so this is a nice example. Okay, so I hope that you guys understood it. Let's go to the next one. I mean, it is a very straightforward one. I would recommend you to try this by yourself. You might want to pause the video and then see if you could figure this one out. Okay, first thing that I want you to do is to figure out the number of chemically different hydrogens. Okay, how do you do that? You draw the condensed structure if necessary. Okay, let's draw it anyway. CH3, 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 and CH3. This is your condensed structure. And then let's look at the chemically different hydrogens. Okay, those are chemically equivalent, and then the other hydrogen will be the middle hydrogen. So these two are chemically equivalent. These two are chemically equivalent. So those are your hydrogens. Okay, so you are expecting two different peaks. You are expecting two peaks. You're expecting two peaks. All right, so now let's look at the chemical shifts. Here's the thing. I mean, all these hydrogens are alkane hydrogens, so nothing interesting is going on. So you can say that all the peaks should be around 1 ppm, right? All these peaks, this peak and the other peak, okay? Both peaks should be around 1 ppm. Should be around 1 ppm, okay? Should be around 1 ppm. And splitting patterns should be interesting. It should be interesting. Okay, so if you take a look at the CH3, I mean the yellow hydrogens, if you take a look at the yellow hydrogens, you have two hydrogen neighbor. Okay, you have two hydrogen neighbor, or a CH group as the neighbor. So it will be like a you can say it will be a triplet because you have two neighbor hydrogens. So it will be a triplet because according to n+1 rule, it will split into two. Okay, it will split into two. And then the middle hydrogen will have a multiplet because you have way too many neighbor hydrogens. You basically have 12 neighbor hydrogens. So you will split into a multiplet. So you are expecting a short multiplet because, I mean, two hydrogens is a smaller number of hydrogens, okay? So this is the two hydrogen peak. The shorter peak is your two hydrogen peak. Okay, this is your two hydrogen peak. Since I don't have the integration lines, the shorter peak, I mean, you can eyeball it. I mean, this is the shorter peak, that is the two hydrogen peak. And this one right here is your 12 hydrogen peak. Okay, and then this is a multiplet. This is a triplet. I mean, it is a little bit complicated, okay, in here, especially because this is a simulated one, okay. But the chemical shifts should be around 1 ppm. That is straightforward. All right, and you have two peaks. One is shorter, the two hydrogen peak is shorter, and the 12 hydrogen peak is taller. All right, okay, let's do another one. Okay, I will let you guys do this by your own, number 5, because it is very straightforward. See if you could figure that one out. Okay, you might want to pause the video. Okay, pause the video and then write the structure down. Okay, and then come back and compare the NMR results. Okay, and number 6 is also something that I have in the handout. I'm going to ask you to pause the video and then write the structure, or you can print out my handout and then compare the NMR and then see if you could get these splitting patterns and also the chemical shifts. Okay, and then the next one is a 2-methyl-but-2-ene. Okay, once again, see if you could figure out how many chemically different hydrogens you have and also the chemical shifts. And finally, also see if you could figure out their splitting patterns. All right, so you might want to pause the video and then check it, or I recommend that you guys print out my handout. And here is a benzene example. Okay, benzene example. Okay, so when you have a benzene, usually those peaks go into benzene hydrogens are typically present around 7 ppm. Okay, 7 ppm. All right, 7 to 8, you can say. And then this is the example for one of that. Okay, and then the last two is 1-bromo-4-methylbenzene. Okay, once again the chemical shifts. By the way, this hydrogen, what do you think the chemical shift is? What do you think the chemical shift is? I mean, it is a vinylic. I mean, this is a CH3 group, of course. This is a CH3 group. Okay, and then those hydrogens are actually next to a vinylic group. Okay, you have a vinylic group. So whenever you have a vinylic group, how much do they add to the chemical shift? It is adding +1, right? It is adding +1 ppm. So baseline is 1 ppm and you are adding a +1, so you are expecting the peak to be around 2 to 3 ppm. Okay, 2 to 3 ppm. That is what you see here. Okay, that is what you see here. All right. So next, what I'm going to do is, we already spent like 25 minutes on these examples from the handout, but next I'm going to do your lab. Okay, I want to see if we could solve the examples that I have listed in the lab. All right. So in this handout, I have given you a couple of different type of questions. In this first example, I have given you 4 similar organic structures, and I want you to match the NMR with the appropriate NMR to each of these structures. So when you are approaching a question like this, what I would recommend you to do is to figure out the chemically different hydrogens so that you can figure out the number of peaks. Okay, so you will figure out the number of peaks and their chemical shifts. Okay, so the first thing that you will do is you will figure out the number of peaks. How? By looking at the chemically different hydrogens. And then second, you will figure out the chemical shift. Okay, you will basically try to calculate the chemical shift. And then once you have that, you can also look at the splitting patterns. Splitting patterns for each of these peaks. All right, so let's take a look at it. So in here, the structure A has a CH3 group. So these hydrogens are chemically different from the CH2 group next to it. And then you have another CH2 group right here. Okay, and then of course you can say that benzene hydrogens are chemically equivalent. Okay, you can assume that benzene hydrogens are chemically equivalent, even though they are slightly chemically different. You might see a multiplet for the whole thing. Okay, and honestly, these hydrogens are somewhat chemically equivalent. Okay, because the structure is balanced in both sides, so these hydrogens are chemically equivalent. So in this structure, how many peaks are you expecting? You are basically expecting 4 peaks. 3 peaks for the CH3, CH2 and CH2, and then 1 peak for the benzenes. So you are basically expecting, you can say, 4 peaks. Do the same for the others. Okay, do the same for the others. You can pause the video and then identify the chemically different hydrogens. All right, so I have highlighted all the chemically different hydrogens. As you could see, all these 4 structures have 4 chemically different hydrogens each. Okay, so you are expecting 4 peaks for each of these structures, and that is our first scope, right? We want to figure out the number of peaks. Now we have done it. That may not distinguish any of these molecules. Just by figuring out the number of peaks will not help you to figure out the molecules. So the next thing that we are going to do is to figure out the chemical shifts. Okay, this should definitely help you in identifying. This should definitely help you in identifying the spectra. Okay, so let's figure out the chemical shift for all of these hydrogens, and I'm going to pause the. I'm going to ask you to pause the video and then see if you could come up with it by yourself. Okay. All right, so first let's look at the first molecule. Okay, first let's look at the first molecule A. So the CH3 group right here has a vinylic group next to it, right? It has a vinylic group next to it. So vinylic groups are +1. Okay, they are +1. So you are adding +1 to 1. Okay, so it is 1 + 1. It is around what? It should be around 2 ppm. It should be around 2 ppm. So these yellow hydrogens should be around 2 to 3 ppm. And then the orange hydrogens. So basically it should be around 1 ppm. Okay, but you have a vinylic group, actually 2 vinylic groups. Okay, you basically have 2 vinylic groups next to each other. So therefore you expect, each vinylic group will add how much? +1, right? So this will be 1 plus 1 plus 1. So the chemical shift should be around 3 to 4 ppm. 3 to 4 ppm. Okay. And next up is benzene hydrogens. Benzene peaks are typically around 7 ppm. Okay, 6 to 7. So typically benzene peaks are around 7 ppm. So they should be mostly similar. Okay, they should be mostly similar for all. So if you see a peak around 7 ppm, that should be the benzene peak for all hydrogens. But the next peak that I am interested in studying is the CH2. Okay, so typically the baseline is 1 ppm. Chlorine will add 2 ppm, and then the benzene will add another 1 ppm. So the total will be 4. So your peak could be around 4 to 5 ppm. 4 to 5 ppm. All right. So these are the peaks that I am expecting for molecule A. Similarly, I am going to write. I'm going to pause the video and I'm going to write the chemical shift that I'm expecting for all the other hydrogens in the other 3 structures. Okay, all the other peaks in the other 3 structures. So I hope that you will do the same. All right, so I have completed all the chemical shifts for each of the structure and each of the hydrogens. Okay, so as you can see, I have given you the numbers that I have added to get the appropriate chemical shift for each of these hydrogens. Okay, so you can pause the video and see if you got the same results. Okay, so next step is to actually take a look at the splitting patterns. But here's the thing, most of these hydrogens do not have a immediate neighbor hydrogens. So therefore the splitting patterns are insignificant. Okay, you don't have to worry about the splitting patterns because these hydrogens do not have an immediate neighbor. Okay, so if you don't have immediate neighbor hydrogens, most of the times we don't have to worry about the splitting patterns. So now since we have all the chemical shifts, now we can take a look at the NMR and then figure out the appropriate structure. Okay, so let's first take a look at the first one. Okay, let's first take a look at the first NMR, and then in this NMR, okay, you have a peak from 3 to 4. Okay, so you have a peak from 3 to 4 ppm. And then you have 2 peaks. Okay, so one peak right here, another peak is right here. Okay, so this peak right here, both these peaks are around 4 to 5. Okay, 4 to 5 ppm, 4 to 5 ppm. Okay, so that's that. And then these are right here, these peaks right here are benzene peaks. These are your benzene peaks. Benzene peaks. Okay, so let's look at the structures and then see if we have a match. Okay, let's look at the structures and see if we have a match. All right, so 2 4 to 5 peaks, and then 1 3 to 4 peak. All right, I think I have a match. Okay, which is this one right here, B. Okay, B has 2 4 to 5 peaks. B has 2 4 to 5 peaks, and then 1 3 to 4 peak, and of course some benzene peaks. Okay, so this NMR looks more like B. This NMR looks more like B. All right, let's look at the next structure. Okay, in here, so we have 2 peaks around 4 ppm, 4 to 5 ppm. Okay, so we have 2 peaks around 4 to 5 ppm. 4 to 5 ppm, and you have one peak around 5 to 6 ppm. Okay, this peak is around 5 to 6 ppm, and then of course you have a benzene peak. This right here is your benzene. Okay, so don't read too much into benzene at this stage. Alright, so let's take a look at it. So you have two peaks from 4 to 5 and one peak from 5 to 6. Okay, I think we have our match right here. C seems to be the match. Why? Because you have two peaks from 4 to 5 and then one peak from 5 to 6. Okay, 5 to 6. So C is the match. This right here is a match, a perfect match for C. And here is the structure for C. Okay, so this is a match. So let's take a look at the third structure. In the third structure, as you can see, we have four peaks. This right here once again is our benzene. That is our benzene. Don't worry too much about it. And then here we have a peak between 6 to 7 ppm. And then right here we have a peak from 3 to 4 ppm. And then this peak right here is between 1 to 2 ppm. Alright, so we have to see if we have a structure that matches these details. So we need a peak between 1 to 2, 3 to 4 and 6 to 7. Okay, so let's go up. I think I found it. It's D, right? It's D. We have the 6 to 7 peak, we have the 3 to 4 peak, and 2 to 3 peak. 2 to 3 peak. Okay. There is a little discrepancy for the 1 to 2 peak. Okay, let's go back and see, because I think it was 2 to 3. Okay, yeah, but I mean I don't see any other structures having a peak around I mean A and D are the other two that is left, but as you can see they both don't have a peak from 6 to 7. Okay, I mean this one is a 4 to 5, so I would say D is the better structure. Okay, D would be the better structure. All right, for this one D would be the better structure. And here is the structure. Okay, here's the structure. Once again, this peak is responsible for the 6 to 7 peak, and then this peak, right, these hydrogens are responsible to 3 to 4 peak, and the CH3 group will be this. All right, that is D. And the remaining structure should be this, but I mean we don't want to do that. We want to see if we can still analyze it. Okay, see if we could still analyze it. So we are expecting, of course the benzene peak is common to everything. Okay, here is your benzene, and then you have to have a peak around 2. I mean I don't think we had a 1 to 2 peak, so this should be the 2 to 3 peak, but it's okay, 1 to 2 peak. And then you should have a peak around 3 to 4, and this peak right here is 4 to 5. Right, so these are the peaks that we have. Okay, 1 to 2 ppm, 1 to 2 ppm. I think it should be 2 to 3. Okay, it should be 2 to 3, and 3 to 4. And 4 to 5. 4 to 5. Okay, so let's go and verify it. I'm pretty sure this is A, but we want to verify it. Okay, we want to verify it, of course. Well, that is A. Why? Because here is your 4 to 5 peak, 4 to 5 peak, 3 to 4 peak, and 2 to 3. I mean this peak is actually in your NMR, it is at 1 to 2. I mean in both these cases, D and A, we saw the same thing. but the other two peaks match. Okay, 3 to 4 and 4 to 5. 3 to 4 and 4 to 5. All right, so the structure is A, and yeah, this is the structure. Okay, so let's match them once again. 1 to 2, or ideally it should be around 2 to 3 in our approximation, but I mean this peak right here is the 3 to 4 peak, and then this peak right here should be around 4 to 5. Okay, so every peak matches, so we got our answer. I think the next up is also a similar exercise. Okay, next exercise is also very similar. You have 6 similar organic structures. I want to figure out the number of peaks. I want you to figure out the number of peaks, and I want you to figure out the chemical shift for each of the chemically different hydrogens. And then finally, I want you to tell me the splitting patterns and then figure out the structure. Okay, so pause the video and then see if you could at least get the chemically different hydrogens or the number of peaks and then the chemical shifts. See if you could do that. Pause the video now. Alright, so I hope that you guys had time to figure out the number of chemically different hydrogens. So I have highlighted the chemically different hydrogens in different colors. Okay, red, blue, teal and purple, I guess. Okay, so basically each of these structure has 3 chemically different hydrogens, so you are expecting 3 peaks in proton NMR. Okay, in proton NMR you are expecting 3 peaks. Now I want you to calculate the chemical shift for each of the structures. Now I want you to calculate the chemical shift for each of the hydrogens. Okay, so you might want to pause the video again and then see if you could do this. Alright, so let's look at structure A. So I have labeled each of the peaks. Peaks and their chemical shifts, expected chemical shifts, of course. As you could see, whenever there is an oxygen as the neighboring atom, okay, or if there is an oxygen directly attached to the carbon that contains the hydrogen, you are adding a 2. If it's a double bond, then the hydrogen becomes a vinylic hydrogen, you are adding a 1. Okay, so that is basically everything that you need to do here. And I have highlighted all the peaks and of course a couple of structures, C and F and D. Actually all these 3 will show splitting patterns. Why? Because you have neighboring hydrogens. So whenever you have neighboring hydrogens, you will show splitting patterns. But every other structure, A, B and E, those 3 structures will not show any splitting patterns. Why? Because the hydrogens are not neighboring. Okay, so the hydrogens are not neighboring, so they will not have any splitting patterns. So you might want to pause the video and check your answers with my answers. Okay, and they should pretty much match with each other. Okay, so let's see if we could find structures that match with these structures. Okay, so you might want to, I have given you 6 NMR structures. Okay, so the first one right here has a splitting pattern. So if it has a splitting pattern, it should only match with C, D or F. Okay, so you already narrow your search to C, D and F, right? So you are narrowing your search to C or D or F. This one does not have a splitting pattern, so it is either A, B or E. A, B or E. So if you have a splitting pattern, it will be C, D or F. If it does not have a splitting pattern, it will be A, B or E. Okay, similarly you can label all the NMR structures. Okay, and then we will start our analysis. In structure A, you have a triplet around 1 ppm, or you can say 1 to 2. Okay, you have a triplet around 1 to 2 ppm, and it's a triplet. Okay, it's a triplet. All right, so that is your first peak, and then you have another peak around 2 ppm. Okay, so you have another peak around 2 ppm that is not split. It's a singlet. Okay, it's a singlet, so it is not split into multiplets. And this right here is a quartet, and it is between 4 to 5 ppm. All right, so now what we are going to do is we are going to match these three peaks with C, D and F. We are going to match these peaks with C, D and F. Especially when matching them, you might want to worry about this CH. I mean, by the way, this is a chordate, of course you know that, okay, because it is split into 4, but this is a CH3 group. This right here is a CH3 group. This right here is a CH3 group. And also this triplet peak is responsible for a CH. Yeah, see, this is actually the CH3, this is the CH2. I'm sorry about that. Okay, so your neighbor has 3 hydrogens. This is a quartet, so that means your neighbor has 3 hydrogens. So the neighbor is right here. Okay, so this is a CH3, this is a CH2. Okay, so which CH2 has a peak around 4 to 5? Let's take a look at it. So as you can see, I mean, the only 2 groups with a CH2, CH3 that are, you know, neighbors, okay, a CH2 and a CH3 that are neighbors are going to be C and D. And among these two, the best match is actually C. Why? Because you have a CH3 group at 1 ppm and then you have a CH2 group around 3 to 4, okay? So all these matches with this one, so this will be C, okay, this will be C. So we already completed C, okay, this will be C. Here is your 1 to 2 ppm, okay, it's actually 1 ppm in the NMR, I mean in the analysis, okay, so that is that. And then it says 4 to 5, but of course, I mean, in our analysis it says 3 to 4 and this is very close to 4, so you can say it is 4 ppm, okay, you can say it is 4 ppm. And you have a 2 ppm peak as well, okay, you have a 2 ppm peak as well right here in the C, okay, so that is the best match for our structure, that is the best match for our structure. So we have already figured out the first one. So let's take a look at the second one. Okay, so it does not have a splitting pattern, so it should be either A, B or E. Okay, so you have a peak around 2 ppm. Okay, so you have a peak around 2 ppm, and then you can see this is between 3 to 4 ppm, and this one right here is around 4 to 5 ppm. Okay, so these are the splitting patterns, okay, these are the splitting patterns. So what we do next is we are going to go back and look at the structures and figure out which one it is. Okay, all right, so you have a peak around 2 ppm and then 3 to 4 and then 4 to 5. So by comparing the splitting, I mean chemical shifts, I think the best suited structure will be A. A will be the most suitable structure for the peak that we just analyzed, okay, this for the spectrum. All right, so A will be the most suitable structure for the number 2 NMR. All right, so in the third one, we already assigned C. So we don't have to worry about C anymore. Okay, so let's erase that. So we have to make a choice between D and F for this particular structure, and this is a very straightforward one. Why? Because I mean you have a doublet, okay, you have a doublet and then you have a quartet. Okay, so to get a 4 peak, okay, you have to have a CH3 neighbor. Okay, so this guy right here has a CH3 neighbor. Okay, so this will be the CH3 neighbor. And then to get a doublet, you have to have a CH neighbor. Right, so this is a CH3 right here. So this peak right here is a CH3. Okay, and then this quartet is a CH. So there was only one such structure. You don't even have to look at the other things, because only one structure gave a doublet and a quartet, which is F. So this structure, we can easily figure it out by the splitting pattern. This one is a quartet and it's a doublet, and only one structure gave a doublet and a quartet, which is F. All right, so that's how you do it. So we have already figured out 3 structures, and then I would let you guys figure out the structure 4, 5 and 6. Okay, I will let you guys give you some time to figure out structures 4, 5 and 6, and I will give you the answers. All right, actually identifying the last 3 is relatively easy, because you can easily remove the structures that you already have identified, and then the remaining structures will sometimes easily give you the answer. We already figured out the other 2 splitting patterns, this other 2 structures with splitting patterns. So D will be the remaining answer, which will have a quartet and a quartet and a triplet. So splitting pattern itself will give you the answer for this one. And then if you compare the ppm values, you will figure out this is E. And also B is very unique because it has a very high chemical shift. So it has a hydrogen at a d-shielded hydrogen at around 6 ppm. So there's only one such structure, which is B. All right, with that we are going to conclude this video. I hope that you understood how to predict structures using NMR spectra, or basically how to predict NMR structures or NMR spectra based on structures. So this basically should give you a nice idea on that. So let me know if you have any questions. Okay, you guys have a good one.